All right, it is. So 8.1, we had parametrics. We spent a couple days on it, parametric derivatives, parametric integrals, and now we have kind of another topic that we're going to spend maybe 2-3 days on, polar. Okay, now polar intro is not an intro to anything that's cold, but it's just another way to navigate through two-dimensional space. What we've been doing has been rectangular coordinates. Okay, so let's review rectangular coordinates. Let me just add a page here. You don't have to write this down. But since you were in Algebra 1 and you learned about the Cartesian plane, you've been navigating through space using rectangular coordinates, all right? So if you had a point over here, you can designate from the origin. You can go right a certain amount in this case and go up a certain amount, and then that coordinate would have coordinates of x comma y. And of course, once you have coordinates of x and y, you can start writing functions of y in terms of x. Okay, and that's where coordinate geometry turns into analytic geometry, which is pre-cal. But there's another way to navigate through two-dimensional space, and if you've ever navigated around a globe, you kind of know how to do that already. I could get to that same point x, y, not by designating a distance left and right and up and down, but rather I can designate an angle. I can stand here at the origin, which I'm going to call the pole, like the South Pole or the North Pole, and I can designate an angle that would rotate me like we did in pre-cal, starting off the positive x-axis. I can designate an angle that would rotate me in that direction, and once I'm pointing in that direction, I can then define a distance along that line that I can march out, call it r for radius, to arrive at the same point. All right? So that would be then called a polar coordinate, and we could then define that point as the point r theta is how we're going to write it. Okay, r is the distance along a terminal ray, if you will, that you're going to be marching along a terminal ray that is rotated theta degrees to get to that point. Now, what's neat about polar coordinates is there's many different ways that are equivalent to get to that point. In rectangular, there's only one coordinate to get there. You go right x and up y, and you're at that point. But because of coterminal angles and the way we can rotate clockwise and counterclockwise, there are infinitely many polar coordinates that get you there. You can actually rotate not that way. You could rotate all the way around to here, which would be a different angle, and point in that direction, and then march out our units. Okay? Because theta, I'll call it theta 1 and theta 2, those are going to be called what angles? Coterminal, right. And of course, you can go around infinitely many times and then stop there eventually and do the same thing. Now, we could also do this, believe it or not. In pre-cal, the radius was always positive. But we're going to call the radius now the directed distance. Just like x and y are directed distances from the origin. So we can actually, believe it or not, if I draw that terminal ray all the way through to this side, there's going to be a way to rotate to that terminal ray. And so now I'm pointing in that direction. But if I want to go back to that point, I'm just going to march backwards now. So you could actually rotate to this angle theta and then have a negative radius, which would march in the opposite direction. And similarly, you could rotate in a positive manner, or I'm sorry, a negative manner, and rotate to the same terminal ray. And if you're pointing away from where you want to go, you can just have a negative radius and march backwards. So infinitely many points. But if you can express that coordinate as a radius, directed distance from the pole, we're going to call it, not the origin, then you march out along a terminal ray in the directed distance that has an angle of theta, you can get to that point. All right, so polar coordinates, rectangular coordinates. So here is what a polar grid would look like. On a rectangular grid, you have a bunch of squares. If you draw all the points, these are a bunch of concentric circles. Okay, so you have the pole, which is really what we're calling the origin, and each one of these circles is increasing by 1 unit. So the first circle has a radius of 1, the second one has a radius of 2, 3, and 4, so on and so forth. So you can imagine like hovering above the North Pole and looking straight down, these lines right here would end up being your latitude lines, right, as you kind of see it going around the globe. That's really what it is. So let's go ahead and assume that this point is actually on that line, and let's assume that it's kind of perfectly in the middle. So let's come up with a possible coordinate for that point in polar form. Now, polar form, you have to remember the order. It's easy for rectangular form because it's x comma y, and x comes before y in the alphabet song, and also the alphabet, I'm told. But r comes before theta, is that right? Maybe phonetically, right? But r does come before theta. So here we're going to do, let's figure out first of all what the angle is. We actually find the angle first, even though it's listed second. And that's one of the things we're going to have to get used to. Theta is actually your independent variable. So that's different, right? Because in rectangular form, x comma y, the independent variable is x. It's listed first. R is going to end up being your dependent variable. It's listed first. So it's a little bit backwards. So what would that angle be in radians? That would get me halfway between the first two, or in the first quadrant. Yeah, the easiest angle would be pi fourths. And now if it lands perfectly on that concentric circle, how far would I march out along that line? 1, 2, 3, 4. Good. So that coordinate could have a point known as 4, comma, pi fourths. We are going to be in radians the whole time, not degrees. So there's one possibility. What would be another possibility? Good. 3 pi fourths. 3 pi fourths is going to put me over here. Now, I have to be at least on the same terminal ray that would extend through. So let's do the negative version first. If I want to get to the same terminal ray, I could rotate clockwise, not pi fourths, but negative 7 pi fourths. So if I rotate to negative 7 pi fourths, that gets me to the exact same terminal ray, and now I'm pointing in the direction I want to go. And if you're pointing in the direction you want to go, then your radius is positive. Okay? So there are two ordered pairs that get you to that point, bless you, with a positive radius within one rotation, one positive, one negative. Now, of course, there's two other options within one rotation if you get to the terminal ray opposite it. So if I rotate all the way over here into quadrant 3 through a positive manner, it's not 3 pi fourths, but what? 5 pi fourths. So I can rotate all the way to 5 pi fourths, which I'll write second. And now because I'm pointing in the opposite direction, I need to march backwards, negative 4. Yeah. So that's also equivalent. And then, of course, we have one last one. If I get to the same terminal ray, but this time by rotating clockwise, that's going to be a negative angle. And what's it going to be? Not negative 5, because I'm only rotating through a little more than a quadrant. Negative 3 pi fourths. Good. I'm stopping just short of negative pi. And, of course, because I'm facing away from the point I want to get to, I need to march in reverse. So there are always going to be 4 solutions within one rotation, positive and negative. One with a negative radius, one with a positive radius. And, of course, if you take the coterminal angles to each of these 4 angles, there are infinitely many solutions. Okay? But there's only one rectangular point that gets you to that space. All right? So, we just did example 1. Find other equivalent polar coordinates for the point shown above. But we haven't finished it. Now it says to find the equivalent rectangular coordinate. So, I know that if I'm going to find the rectangular coordinate, let me go ahead and write one of these down. Let's take the simplest one, which would be when they're both positive. Bring it down here. So remember that this is an r and a theta. And what I want to do is find an equivalent rectangular coordinate that gets me to that same exact point. Now what I know is that x is going to be positive and y is going to be positive, but how can I figure out exactly how far? Unit circle. Yeah, very good. Let's get rid of all the noise over here and just leave this. If I, like we did in pre-cal, we go to that ordered pair along that positive terminal ray and we drop a perp, right? We create a right triangle. And I know that this angle is pi fourths. And I know that the hypotenuse is 4. How can I figure out the x and y? Well, first of all, what do I know about the x and y in this case? They're the same, right? But in general, they may not be the same, right? So is there a way to relate x to y in a right triangle with the reference angle? What ratio is that? Which trig function? Well, yeah, sine would not be bad. Sine relates the y to the hypotenuse. Well, which one relates x to y? Tangent or cotangent. We probably prefer tangent. So tangent, remember, of your central angle is y over x. And we also have a way to relate the side lengths to the hypotenuse, which is the Pythagorean Theorem. In this case, x squared plus y squared equals r squared. These are essentially the two equations that you're going to be using when you're going back and forth between rectangular and polar. Because one of them expresses the angle in terms of x and y, and the other one expresses x and y in terms of r. So let's go ahead and figure it out. Let's go ahead and plug our values into, what do I do? Plug theta in? Sure. Okay, so if I plug them into here, I get tangent of pi fourths equals y over x. And so what is tangent of pi fourths? We can evaluate it. It's 1. So I know that 1 equals y over x, which tells me that y equals x, right? It tells me that y equals x. But it doesn't tell me what y and x are. But now I can plug it in over there, right? I know that, let's see, x squared plus y squared has to equal the radius, which we know to be 4. So that's 4 squared. And now since x and y are the same, I could say x squared plus y squared, x squared plus, let's substitute, x squared plus x squared equals 16. So 2x squared equals 8, and x would equal plus or minus the square root of, I did too many things in one there. All right. So x squared equals 8. So in this case, I know which version I want. I want the positive or the negative square root? Positive, because I'm in quadrant 1. So it'll be the square root of 8, which of course is 2 square root of 2. And now that I know x is 2 square root of 2, I can plug it back in over here, and I know that y is equal also to 2 square root of 2. So you could do it that way. So now I know the rectangular coordinate is 2 square root of 2, comma, 2 square root of 2. No, you don't. The other way to do it is to realize that the unit circle, let's talk about that. The unit circle would be this very first concentric circle outside the pole. And that coordinate on the unit circle would be square root of 2 over 2, right? Well, we're looking at a circle that is 4 times bigger than the unit circle, right? And since we're talking about circumference to radius, those are both linear units. So all you have to do is take the ordered pair there, square root of 2 halves, square root of 2 halves from the unit circle, and multiply each ordered pair by 4, and it works, okay? Now, here's another way to do it if you don't want to do it kind of by a system of equations. Can we express x and y in terms of a trig function, r and theta? Yes, and it's what you said a little while ago. Remember, let's do this. Remember that sine of theta is y over r, and cosine of theta is x over r. So this kind of will have a very similar feel to what you did in physics. If I solve the top one for y, I get y equals r sine of theta, and x equals r cosine of theta. So here's actually a preferable way. The coordinate x, y, if you know the point in polar coordinates, is just r cosine of theta times r sine of theta. And you don't have to do it by a system of equations anymore. All right, let's see if that works. Our radius is 4. Our angle is pi fourths. So what's 4 times cosine of pi fourths? Well, it's 4 times the square root of 2 halves, which is 2 square root of 2. Same thing over here. 4 times sine of pi fourths is 4 times square root of 2 halves, which is 2 square root of 2. So this is a little bit more useful when you are converting directly from polar coordinates to rectangular coordinates. All right? These equations up here we'll revisit again. They're a little bit more useful actually when we're going the opposite direction. Okay? So why use polar coordinates? Rectangular coordinates seem to be working okay up to now. We haven't even seen polar coordinates. Well, first of all, it's nice sometimes just to have another way to do things, right? You don't want to use Uber? Use Lyft, or call a taxi, or walk, or ride a bicycle, right? Or thumb a ride. Don't thumb a ride, that's dangerous. Or drive yourself, right? So having different options is sometimes kind of nice. And sometimes one method is actually more suitable for the task than another method, right? Yeah. I'm trying to think how that would relate to like using Uber versus Lyft. Yeah, I don't know. Yeah. Maybe if you're downtown New York and all you see are yellow cabs, maybe you don't call an Uber, right? Because there's a cab right there. So maybe a yellow cab is better. But if you're in some remote region where there's no cabs, maybe Uber would be the way to go. So that's kind of the same idea here. Polar coordinates are actually more useful for graphs that are not functions of x. That is, for graphs that fail the vertical line test. That is, elaborate curves, essentially. Polar coordinates can capture a graph that doesn't pass the vertical line test in a much simpler equation than a rectangular function can. And kind of vice versa. If it's a simple graph that is not very curvy, rectangular coordinates do a better job of capturing the equation with a simpler equation. And polar curves sometimes are more elaborate, as you shall see. All right? So let's go ahead now and switch from just coordinates. Let's switch to graphs, because once we have rectangular equations, x comma y, we can start looking at graphs of y in terms of x. Here we have polar coordinates, so we're going to be looking now at functions in terms of theta. Okay, so we're going to be looking at functions of the form r equals f of theta. So again, keep in mind that when we say f of theta, that implies that theta is our what? Independent variable, and r is like our old y, it's the dependent variable. But it's backwards because our coordinates, we still typically list them as r comma theta. All right, so it's backwards. All right, so what does the graph of r equals cosine of theta look like? Well, let's go ahead and do like what we did in Algebra 1. Let's kind of just pick some random independent variables, compute the values, and plot the radii. All right? So we have the pole, which is the origin. The positive x-axis is called the polar axis. For what it's worth, it's the positive x-axis. And the y-axis is called the line theta equals pi halves. That's the y-axis. Why is it called theta equals pi halves? Because when you rotate on the unit circle, that gets you on the y-axis. So that's just a little bit of vocabulary. So let's go ahead and plot some points now. I'm going to get rid of all that. Let's choose 0. Let's choose some nice angles. So when theta is 0, I'm pointing due east, right, on the positive x-axis. That's where theta equals 0. What is the radius when theta is 0? What's cosine of 0? 1. So now that I'm pointing due east, I'm going to march out along the positive x-axis 1 unit. There I am. Now I could choose any angle I want. As I rotate, pi 6 is square root of 3 halves. That's an ugly number. Pi 4 is square root of 2 halves. That's an ugly number. How about pi thirds? Okay, so I'm going to draw my little radial line as a dotted line. So I'm rotating up here to pi thirds, which is 60 degrees. What's cosine of pi thirds? 1/2. Okay, so now I'm going to march out along this line a half unit. I don't have my concentric circles drawn, do I? I don't really need them. I can kind of infer where 1/2 would be, because if I connected this point 1, 0 and the point 0, 1, that would be a radius of 1. I want to come in about halfway, so about right there. You only march out about a half unit. Okay? Now let's rotate all the way up to pi halves. So again, I'm going to draw a dotted line. I'm pointing now due north. The angle is pi halves. What's cosine of pi halves? 0. I have now hit a polar 0. Let me write that down. A polar 0 is when the radius is equal to 0. A rectangular 0 is when y equals 0. Always when the dependent variable is 0. Those would be x-intercepts, right? A polar 0 is always going to be at the origin, and you're trying to find the angle that you rotate through that gets you a radius of 0, okay? So notice what I've done as this thing rotates through 90 degrees, essentially, from 0 to pi halves. my radius has gone from 1 and it's decreased down to 0. So there is some idea of direction as well as path. We're tracing it out, in this case, counterclockwise. All right, let's keep rotating. What would be the next bicycle past 90 degrees from the unit circle? 2 pi thirds. So if I'm pointing in this direction, 2 pi thirds, what is the radius? What's cosine of 2 pi thirds? Negative a half. Okay, so now I get to do what? I get to retreat in the opposite direction, 1/2 unit. So that's going to put me right here. Notice the point above and the point I just graphed are symmetrical across the x-axis, or symmetrical across what we call the polar axis. All right? Let's rotate down to pi. So now I'm pointing due west at pi. What's cosine of pi? -1. So if I'm pointing due west and the radius is -1, I have to step backwards 1 unit, and guess where I'm at? I've come full circle, right? I'm back over here. So this thing comes around full circle. So notice what I've done is as theta has rotated from 0 to pi, I have traced out a counterclockwise circle whose diameter is what? Is 1, okay? Is there a 1 anywhere in my function equation? Kind of. There's a 1 in front of cosine. Is that the diameter? We'll have to see after lunch, okay? This is interesting, okay? So the graph of r equals cosine theta will always end up being a circle whose diameter is the amplitude of cosine. And of course, cosine is associated with which variable on the unit circle, x or y? X. It will always have x-axis symmetry then. If it's cosine, it'll have x-axis symmetry or polar axis symmetry. All right, we'll do more with this after lunch. Have a great lunch.